Okay, this is the second part of AQA A-level Chemistry Paper 2. This is the June 2017 paper. Okay, so first question about nitrobenzene. Nitrobenzene reacts when heated with a mixture of concentrated nitric and sulfuric acid to form a mixture of 3 isomeric dinitrobenzenes. Write an equation for the reaction of concentrated nitric acid to form the species. So we're talking about the electrophile here, okay, NO2, which can attack, that then is going to attack the benzene ring. Normally we have it just reacting with a benzene ring, but here we've already got a nitro group stuck on there. So now it says an equation. I always prefer to write 2 equations here. So, and if you look in the mark scheme, they always accept this. So nitric acid plus H2SO4. So the nitric acid actually acts as a base and accepts a proton from the sulfuric acid. So that becomes H2NO3 plus. And the sulfuric acts as an acid, so it loses a proton, becomes HSO4 minus. Now be careful not to say that it loses 2 protons to form that. It doesn't form the sulfate ion. It can only lose 1 proton because concentrated nitric acid is not a brilliant base. And then what happens is H2NO3 loses water to form the electrophile and water. I prefer to write it as 2 equations because it's clear then the role of the this as the base and this is the acid, because they quite often ask that as well. Okay, so name and outline a mechanism for the reaction of this species with dinitrobenzene to form 1-dinitrobenzene. So this is of course electrophilic substitution, and we want to form, so we start off with nitrobenzene. And it says here we're going to form 1,3. So we've got 1, 2. So we're going to stick the second nitro onto there. That's the product we want to go for. Right, so let's draw that. Here's the electrophile. Sorry, NO2 there. Right, a pair of electrons come out of the delocalized ring onto the nitrogen and form a bond there. That's the first step. So that's going to form this intermediate. NO2 is still on there. We've got NO2 on there. And we usually show there's a hydrogen attached there. There's hydrogens attached to all of those, of course. And we show the delocalization system has been broken because a pair of electrons left it. And it's usually, we say it's been draw from that carbon to that carbon. And of course, this whole intermediate is going to have a positive charge on it, which is shared on the on the benzene ring, okay, which stabilizes it, and then we are going to get a the pair of electrons. We're going to lose a proton. That pair of electrons goes back into the ring to form the product. So that's pretty straightforward, and we get a proton coming off as well, and that mechanism is called electrophilic substitution. This is the electrophile substitution, because you swap a hydrogen for that NO2 essentially. Okay, so here now we've got 2 isomers of dinitrobenzene. Okay, this one would be called 1,2-dinitro, this one here, and this one would be called 1,4-dinitrobenzene. Okay, and going to carry out thin layer chromatography. Okay, the TLC plate has been coated with a polar compound. Okay, it says, and hexane is used as the solvent. So the hexane is not, obviously that's non-polar. It's a non-polar solvent. Okay, the start line, and draw in pencil the final position line and the position of the spot. Okay, now let's just think in chromatography. Things are separated because they've got different affinities for the stationary phase, which in this case is polar, and for the mobile phase, which in this case is non-polar. So you would expect non-polar things to move more with the solvent. They'd move further up here, so they'd have bigger RF values. Polar compounds would like the stationary phase better, so they're going to stay further down here. They have lower RF values. Okay, so there's probably going to be some questions about that in a minute. Okay. Use the chromatogram to deduce the RF value. Okay, so how do we do that? Well, I did this on a bit hard to draw it on the screen, but the RF value, of course, is equal to the distance moved by the spot divided by the solvent front distance. And I measured that to be 41 millimeters on the real paper, and this was 62 millimeters, 66 millimeters, sorry. So the RF was 41 over 66, and that is equal to 0.62. So 1 mark for working out the RF value of a spot there. That's quite easy. Yeah. Okay, 1 mark, we have sort of discussed that before. In what general terms, what determines the distance traveled by the spot? So it's how much the affinity, rather than the affinity, or the relative affinity for the mobile phase, which is the solvent, and the stationary phase, which is the TLC plate, the solid, which in this case we are told is fairly polar, and when the mobile phase is hexane, which is pretty non-polar. Okay, right. To obtain the chromatogram, the plate was held by the edges and placed in the solvent and the beaker in a fume cupboard. A lid was replaced on the beaker. Give another practical requirement when placing the plate in the beaker, and the only one I could think of, which is the one that's in the mark scheme, is that you should make sure that the level that the plate, here's your start line, the level of the solvent has got to be below that, because if it wasn't, it just washed the spot off into the solvent. So that's the answer to that one. Right. A second experiment, TLC, was carried out using 1,2-dinitro and 1,4-dinitro. Okay, so let's just write those down here. So 1,2 is going to be the two nitros next to each other, and 1,4 is when they're opposite each other. Okay, in this solvent, the RF value of the 1,4-dinitrobenzene was found to be greater than the 1,2. Okay, the solvent they used as well, it said, was hexane, non-polar. Deduce the relative polarities of 1,2 and 1,4-dinitro and explain why the 1,4 has a greater RF value. Well, let's have a look at these molecules. We can see here that the 1,4 is symmetrical. So that means it's not going to be terribly polar. Yet you've got all these electronegative elements up there, drawing charge towards them. But you've also got one at the opposite end, and of course that's perfectly symmetrical. So there's no dipole for that molecule. So it's non-polar. So that's going to like the hexane better, and like the solvent better. So that's going to move with the solvent. That's going to give it a bigger RF value. Have a look at this one. It's not symmetrical. You've got all these electronegative groups on one side of the molecule, so that's obviously going to be pretty delta, and the minus on that side, and so obviously it's going to on that side. So that will have a permanent dipole. So that is going to have a greater affinity for the TLC plate, which is being coated with a polar substance. So it's going to have a lower RF value. Okay, so that's going into slightly more detail than you probably need to for 2 marks. You have to say that, you know, the polar one is not going to move so far. It's going to stick to the plate better. Right. A third TLC was carried out 1,2-dinitrobenzene So remember, this is the polar molecule. Use the same identical plate. So in other words, the plate is polar. But the solvent used contain a mixture of hexane and ethyl ethanoate. Now, hexane is non-polar, but ethyl ethanoate is polar. It's got carbonyl groups and oxygens, and it's got the ester group in it, hasn't it? So this is a little bit more polar. Okay, so that means we would expect the 1,2 to like the solvent more. Greater affinity for the solvent. That means it's going to move further in the solvent. So that means it's going to be a bigger RF value. Now it says here, the student says the RF value in this experiment would be greater. Is he right? Yes, he is right. Justify your answer. Well, 1,2 is a polar molecule. We've made the solvent more polar by introducing ethyl ethanoate. So it will travel further, so the RF value will be greater. Okay. Right. Now this is a biochemistry question. Use the data booklet to help you answer these questions. Okay, DNA exists as 2 long strands of nucleotides in the form of double helix, blah, blah, blah. Okay. A deoxyribose molecule in a strand of DNA is shown. Name the types of groups attached to the 2 deoxyribose at position X and Y. Well, you've got to really just know this, that this is the this is the base, either A, T, G, or C is attached to that carbon there. It's probably good to know the numbering. That's carbon number 1, 2, 3, 4, and 5. Now, what is attached to 5 and 3 in DNA are phosphate groups, but it's only asking us 3 at Y, so the answer there is we have a phosphate group. And of course, that phosphate is going to form a link to the next nucleotide along. Okay, so where I've just drawn there, that's going to join on to this bit of the nucleotide above it. So that's just about knowing your structure of DNA, really. 2 marks there. Now this question here for 2 marks is horrendous, really. Okay, right. So now in DNA, double helix, the 2 strands of double helix are linked by hydrogen bonds, and we all know that, of course, that A will pair up with T, and G will hydrogen bond to C. Now complete the diagram below to show that the other molecule and the hydrogen bonds between it and adenine. Okay, so this thing, I've just copied the bases out here. We've got, this is adenine, you can see there. And so that is going to hydrogen bond to thymine. But unfortunately, they have, if you've drawn the adenine, if you notice, it is drawn the opposite way round to how it is drawn on your data sheet. So you've got to transpose everything in your head, which is extremely difficult to do. And for 2 marks, it's an awful lot of work. Okay. And what happens is, right, I'll draw it in correctly here. And you can probably hear I'm rustling paper because I don't know without copying it, because it's very complicated. Okay, so you've got, that's 1 hydrogen bond here to the hydrogen of the thymine. Okay, and there is the ketone there, and that is hydrogen bonding to that hydrogen there. Right, I'll just finish the rest of this. So we've got CH3 there, and we've got the other carbonyl there. Now you can see there that like that bit there has now become that bit there. So you've had to twist the whole thing round, which is really difficult. And for 2 marks, if you can do, mark a minute. If you can draw that in 2 minutes, then you've got a very good knowledge of. I think many people got that right. I've just drawn the real base pairing here because on the data sheet, if they stick with them that way around, look, the thymine and the adenine, all I've done is I've got thymine and I've got adenine, and without having to rotate or anything, you can draw them quite easily, that pair there. The cytosine and the guanine, without having to rotate, you can just do that with them. I haven't rotated any of them, and that's reasonably okay. But if they're going to start giving diagrams where they've actually transposed, they flipped it over the other way around, it is very difficult. So good luck with that. Okay, for 2 marks. Right, on to question 10. 6 isomers of C6H10O2. Give the full name of isomer P. Right, so now they've drawn out that double bond. Now we need to bear in mind that there's a possibility of a geometric isomerism, EZ. So we're going to have to give the full name. We have to give them which one it is. So we've got 1, 2, 3, 4, 5. Right. So it is butane. It's pentan something or other. So it is, I'd say, and we've got a methyl there. So it is 2-methyl pent 2-enoic acid. And then we've got to decide, is it the E or the Z isomer? Well, let's look at this carbon here, number 2, which is the highest priority group. It's this one because it's heavier, bigger molecular weight. And which is the highest priority group on carbon number 3? It's that one. So the 2 high priority groups are on the same side, so it is actually the Z, the together isomer. So Z2-methylpentene 2-oic acid. So, all right, a mixture of P. Let's get a calculator here. A mixture of P was mixed with an excess of oxygen, okay, and the mixture ignited. After cooling to the original temperature, the total volume of gas was 335. Right, so we're going to have to use the ideal gas equation here, right? Right. So let's see what we're doing then. P. They're going to ignite the sample of it, and you get 335 centimeters cubed of gas. Okay. Okay, so then you pass it through sodium hydroxide, and the volume of the gas decreases to 155 centimeters cubed. So that means the volume of CO2 is going to be 335 minus 155. That's 180 centimeters cubed of CO2. All right, both gas volumes were measured. Okay, so at 25 and 105 kilopascals. Write an equation for the combustion of P in an excess of oxygen and calculate the mass of milligrams of P used. So let's work out the number of moles of CO2. That's what we've got to do. So we've got PV is equal to nRT. So N is equal to PV over RT. Right, the pressure, we've got to be really careful with the units here. We can't have kilopascals, we've got to turn that to pascals, so that's 105,000. The volume, 155 centimeters, we've got to turn that into meters cubed, so divide by 1,000,000, so that's 155 times 10 to the minus 6. R is 8.31, and the temperature, 25 degrees C, convert to Kelvin, that's 298. So we calculate the values there. We have got That gives us N is equal to, the moles of CO2 is going to be 6.572 times 10 to the minus 3. Okay, now P has got 6 carbons in it. Okay, so the formula of P, well, it's C6, blah, 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 blah. So that means 1 mole of P is going to give us 6 moles of carbon dioxide. So if we've got that many moles of carbon dioxide, how many moles of P did we have? So moles P is going to be that divided by 6. That gives us 1.095 times 10 to the minus 3. All right, now we should write an equation for the combustion of P and use it to calculate. So let's write a full equation. So P is C6 H 10 O2. I'll just check that is H10. Pretty sure it is. Yeah, we've got 3. That's 5, 6, 7 plus 3 makes 10. Yeah, that's fine. So write an equation for the combustion of P. So we need oxygen. It's going to give us 6 carbon dioxides, 5 waters. Right, so how many oxygens are going to need? We need 6 times 2. We need 12 oxygens for the carbon dioxide, and we need 5 there, which makes 17. So that is 8.5 O2 to balance it. Right, now the number of moles of P we've worked out was that many. So what is the mass of P? Well, moles is equal to mass is equal to moles times the MR. The MR of this stuff, well, it's going to be, it's going to be 12 times 6 plus 10 plus 2 times 16, 114. So that's going to be 1.095 times 10 to the minus 3 multiplied by 114. That's equal to 0.1248 grams, and it asks for us in milligrams, so let's do that. So that's equal to 0.125 milligrams to 3 sig figs. All of our data is given to 3 sig figs, so we should do that. 0.125 milligrams of P. That's quite an unusual question, that one, I think. I don't think we've seen one quite like that for a while. Okay, so now we're going on to structure determination using spectroscopy. So we've got Q is a cyclic compound. We've got the infrared spectrum on the left, and we have got the 13C NMR on the right. Now, what is use these spectra to deduce the structure of Q. Now, the first thing I like to do here is look at the carbon hydrogen ratio. We have got we've got C6H10. Okay, now if it was saturated, it would be C6H14, but it's cyclic, so we always lose 2 hydrogens for that, because so that would be, if it was saturated, it'd be 6, but it's not. It's C. So that means we have 1 double bond in there, and that could be a carbon-carbon double bond, or more likely a carbon-oxygen double bond. Okay, so let's have a look at the spectrum, and you can see that the infrared spectrum is a giveaway. This shape here, this very broad bit here, is definitely a carboxylic acid. So we've got a carboxylic acid, and that is confirmed by this peak here, really, because that is very characteristic of the shape and the number of a carbonyl group, which of course you're going to have in a carboxylic acid. Okay, so we've got a cyclic compound. Before we even looked at the carbon 13, let's have a think. A cyclic compound with 6 carbons in it and a carboxylic acid group. So the carboxylic acid group can't be in the cyclic bit. So there's 5, and we could have that. Okay, that's a possibility. Now we can see we've clearly got 4 peaks in this carbon-13. How many carbon environments have we got in this thing I've just drawn here? Well, we've got 1, 2, these two are the same, 3, 4. Okay, so that is a possibility. It could be that. So let's bear that in mind. But just to make sure that's not definitely it, because let's just think we could have a 4 in a ring with the carboxylic acid, and we'll have to have a methyl coming off here. How many peaks would that give us? That would give us 1, 2, 3, 4, 5. So it's not that. Okay, what else could we do with 4 in a ring? We could get rid of that methyl, and the other position it could go in is there. How many peaks would that give us? That would give us 1, 2, 3, 4, and 5. So it can't be that one either. Okay, so it can't be 4 in a ring. The only other possibility it could be is 3 in a ring with 2 side groups on it. So let's try that, just to rule that out. So we've got a carboxylic acid group, and we've got a cyclic group. Just draw it a bit better than that. Okay, now we need to stick 2 methyl groups on that to bring up the number of carbons, and the only places we can have them are there and there. Now, how many peaks have we got there? Well, we've got 1, 2, these 2 are the same, 3, and 4. Oops, 4 for that one. That should be yellow, sorry. So do that in purple, that would be 4. So that's going to give us 4 peaks as well in the Nmr spec, and that's going to give us 4 peaks. So it could be either of those. Let's just check the chemical shift values, see if there's anything obvious there. Well, this 180, this peak at very high, that's due to that one there, because it's near to the electronegative oxygen. And the others are, the other 3 peaks are a bit much of a muchness. They're all in the region where, they're all in this, well, I suppose, actually one of them is not in there. This one here, that is next door to a carbonyl, isn't it? Because that's about at about 40 odd. If it's not, and it can only be as high as 40 if it's not near a carbonyl. So that could be that. This peak here could be that one next to the carbonyl there, or it could be that one there. So with the data we're given, we can't really distinguish between those 2 answers there, and you're allowed either of them in the mark scheme. They're both okay. Right, there's 3 marks going there. I've given way more information than 3 marks, but you just have to pick and choose what you would like to include in your answer there. You probably get, I would imagine realistically, you're going to get 1 mark for that, 1 mark for saying the number of peaks, and then you're going to get 1 other mark for looking at the ppm values and matching them up. It'd be something like that. Okay. Okay, so more Spectra stuff, NMR stuff. Isomers R and S are shown. Although the 13C spectra both show the same number of peaks, the spectra can be used to distinguish by using the ppm values. Okay, now what I'm going to do is I'm going to just grab that ppm data again. Okay, just so we can have a look at it. Rub that stuff out. Okay, now just justify this statement using table C from the data book. Give the number of peaks for each isomer. Okay, so let's just see how many peaks for each isomer. This one, those two are the same, those two are the same, and those two are the same. So that's going to give you 3 peaks. For S, these two are the same, these are the same, and these in blue, these two are the same. So that will give you 3 peaks as well. Okay, now let's look at the ppm. I think I'll do those in a different color so I can talk about them. So let's have those in have these two black, these can be purple, and that can be highlighter. Okay, right, use the, how can we distinguish them? By looking at the ppm values. Okay, well, let's look at R. The blue peaks are going to be very high. They're going to be like at 180 or something. Okay, this one here, aldehydes or ketones, 190, 120. So these are going to be really high, but they're both going to have that peak in it, so that's not going to tell us much. So they've both got one peak at around 200 ppm, so that won't distinguish them. Let's look at R. Now, the red and the green, they're both next to carbonyls, aren't they? So you're going to get 2 peaks there next to the carbonyls, which is typically about 50. Let's say as well, 20 to 50. Right? That's for R. Now, is S going to have, and that will be, well, S won't have 2 peaks in that region, because look, the purple peak here, this is only, that will be the one with, which is next to a carbonyl, so that will be in the range 20 to 50, but you'll only have 1 peak, whereas the highlighter peak, the one I've done in highlighter there, that's going to be lower. That's going to be in the range 5 to 40, and you're not going to see that range 5 to 40 peak in the spectrum for R. So that's how you're going to distinguish them. S is going to have this lower peak, and R won't have it. Okay, I think it goes for 1H NMR on these compounds here. It doesn't. Right, it doesn't, sorry. Okay. 104. Actually, I think I've missed a question out there, and yeah, it does. 105. Yeah, question 105. It asks us about the. It says in the 1H NMR spectrum. Okay, so 10.5 says in the 1H spectrum, 1H NMR, they both have the same number of peaks, but the splitting is different. Give the splitting. Okay, now this is a little bit tricky, this one here, because, right, you think, right, first of all, you're going to think, right, well, they're both going to have 2 peaks in the 1H spectrum, aren't they? So this one is going to have this red. Those two are the same, red. Now, what's the splitting of them? That's going to be a singlet, okay? Because the carbon next door doesn't have any hydrogens on it. Now, these two, this peak is a bit more problematic, okay? Now, it's tempting to think, oh, look at that carbon. Carbon next door has got 2, so it's going to be a triplet, but it won't split it because identical hydrogens don't split. So that will also be a singlet. It will not be a triplet, okay, because they're identical. They don't split each other. Let's look at this one now. Right, so we've got these 2 red peaks. These are the same. That will be the same peak. And what's the splitting of that? We'll look at the carbon next door. It's got 2, so that's going to be a triplet. And these, that's going to give you the same signal, because they're identical. Look at the carbon next door. You've got 3, so that's going to be a quartet. So that will give you a quartet and a triplet, whereas this one here is going to give you 2 singlets. A lot of people will make a mistake about that, thinking that's a triplet. Well, when they're, as I say, when they're identical, they don't split each other. Okay. 10.6. Okay, the action of heat on 5-hydroxyhexanoic acid can lead to 2 different products. Okay. Right. So let's just draw 5-hydroxyhexanoic acid here. So we've got 1. We've got a carboxylic acid on one end, and we've got an alcohol on the other end. Okay. Right. It loses water to form a cyclic compound. Right. That maybe you may be puzzled a bit by that. Maybe not quite so puzzled this. Under different conditions, this forms a polyester. Now, how is it going to form a polyester? Well, the molecules are going to go head to tail, aren't they? Because it's got an alcohol group at one end and a carboxylic acid group at the other end. Hexanoic 1, 2, 3, 4, 5. I've missed one out there. Let's just put another one in there. Sorry about that. And what they're going to do is they're going to go to head to tail, aren't they? And they're going to form okay, sorry, back we are. We're back again. Right, so that's going to do that. And we are going to lose water. And we're going to form an ester. Just rub that out. So we've got the ester linkage there, and there's the new bond, okay? So a repeating unit of that ester, we drew that there. And then I would have to get rid of this bit here. Might ask us for the repeating unit later. Now, so draw the repeating unit, the polyester, and name the type of polymerization. So there's a repeating unit, and it is, of course, condensation polymerization, not addition. Right, now we need to draw T, the cyclic compound. Now, what happens there is it forms instead of going head to tail, the head swallows the tail, and they form, so that's going to form an ester, a cyclic ester. There, we're going to lose that water. Okay, so let's draw that. So we're going to have six carbons. Let's draw this way. Okay, so I'm going to make that is going to be carbon number 1, number 2, number 3, number 4, number 5, number 6, just to label it. So this is going to be carbon number 2 here, 3, 4, 5, 6, and we've got the ester linkage there. So that is T, and then we're going to have to put hydrogens on. CH2, 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 CH2. Okay. Or you can write the skeletal formula if you prefer. Okay, so it forms a cyclic ester or it forms a polyester. (10.6) The action of heat on 5-hydroxy can lead to 2 different. Right, so sorry, it's repeated that. 10.7. Okay. Isomer U is shown. The polymer formed by U and by 5-hydroxyhexanoic acid. Question 6. Both contain ester groups that can be hydrolyzed. Draw the repeating unit formed by U. Right, now this is quite misleading because you think, oh, something to do with polyesters in addition, and it's condensation polymers, but it's not. It's this bit. It's the alkene bit, which is going to lead to the polymer. And and the ester bit is actually not reacting. So let's draw the alkene in like this. We've got hydrogens attached to that carbon. We've got a CH3 attached to that carbon, and here we have got this big ester group. Right, so you're going to get two of those next to each other. Well, we're going to get thousands of them next to each other. Okay, what's of course is going to happen is, and you've got one on this side as well, you're going to break the double bond, and you are going to form a new single bond to that one on that side of it, and a new single bond to that one. So the repeating unit you would draw as being that. Okay. Right. Okay. Now, justify the statement that although both polymer structures contain ester groups, the polymer U is not biodegradable. Right. Now, polyesters are biodegradable. Okay. So I'll just go back to the other one, which is a polyester. Well, let's draw a polyester here. Why are polyesters biodegradable? Right, because they're held together by, if I just draw, that could be something, yeah. And that carries on forever. Why are they biodegradable? Because things like nucleophiles like OH minus, or water in fact, is going to attack that carbon there, which is going to lead to that bond to break. Okay. Now here, the ester linkage, yeah, that can be broken by a nucleophile, but the ester linkage will just chop off that bit there, and you can see that this bit, the polymer backbone, is still intact. It's not affected. Okay, so justify the statement, I would say that the ester in this polymer can be hydrolyzed, can be, react with water and split, but that doesn't lead to splitting of the backbone of the polymer. Whereas in this one here, which is a proper condensation polyester, it would cause the backbone to be split, and so you get split into smaller units. Okay, now I think this is towards this paper. This is the last question, I think. Yep. Oh, not quite. Okay. Right. Explain the difference in base strength of these amines and give the order. Okay. So, right. Let's get the order sorted out first of all. This one is going to be the strongest. This one's going to be the weakest. And this one is going to be the middle. Right. So you probably get 1 mark just for the order, maybe 2 marks for the order. And then we've got to explain it. Now, so in the explanations, you've got a lot of people leave out obvious things. They think, oh, that's obvious, but you actually get marks for saying the obvious things. And if you don't say it, you'll lose marks. Okay, so what you have to say is bases accept H plus ions. And you have to say it's the lone pair on the N atom that accepts protons, okay? Now, a lot of people don't say that, and I think maybe lost 1 or 2 marks. So, you only get 4 out of 6 if you don't say that obvious stuff, okay? Now, why? Let's say why this one is the weakest. E is the weakest. That's the easiest way to say it. That's the weakest because the lone pair on the nitrogen is partly delocalized onto the benzene ring, so it's not as available to attract the H plus ions. Right, let's go to straight why F is the strongest, right? Why, rather than talk about the middle one. F is the strongest because this is a primary amine. Now, it doesn't matter about the benzene ring because it's too far away. It has no effect. This is an alkyl group, and alkyl groups have a slight tendency to release electrons, to release negative charge towards the nitrogen. So the negative charge on the lone pair on that nitrogen is it's got more negative charge, stronger, so it's better attracting H+ ions. And so this one in the middle, it's a bit more tricky to explain this one, but you can say, right, first of all, the lone pair will be delocalized partly because it is next to the benzene ring. But it's a stronger base than E, because you do have an alkyl group attached to it as well, which releases charge. Okay, so that's and as I say, if a lot of people will understand that perfectly, but not get full marks because they don't state that obvious stuff about the lone pair and the protons there. Okay, now definitely the last question now, I think. Amine F can be prepared in a 3-stage synthesis. So put in F there, starting from methyl benzene. Suggest the structures of the 2 intermediate compounds. Okay, give reagents and conditions, equations and mechanism not required. Okay, so we're going to start off with methyl benzene. And we somehow got to get to that. Now, what we've noticed there is that you've added a carbon atom. And usually when we add a carbon atom, make the carbon chain longer by 1, what are we doing? We are reacting it with a cyanide ion. Okay, and that would also explain where this nitrogen is coming from. And if you remember a nitrile, we can convert to a primary amine by reacting it with hydrogen. We can do that. Okay, so we can do that. So the thing is then, we just got to think, how on earth can we stick so we've done the last bit, how can we stick a cyanide, make a cyanide react with methyl benzene? Well, it won't react with benzene, it won't react with that. What kind of things do cyanides react with? Well, they react with aldehydes and ketones. We don't want to get involved with that. There's no oxygen in either of those molecules. They will also react with haloalkanes. Okay, so if we could turn that into CH2CH, then we would probably be, if we could do that, then we would put on the way there. And we can do that, can't we? It's not a brilliant way of doing it, but we can. How can you turn one of those, swap one of those hydrogens for a chlorine? We want to do free radical substitution. I say it's not a brilliant way of doing it because you're going to get a whole mixture of products with free radical substitution, but it's the only way. Right, so we get that, and we are going to turn that into chlorinate it, CH3. And what conditions do we need for that? We need UV and chlorine gas. You need UV because it's a free radical substitution reaction to start it off. So once we got that, then we are going to do a nucleophilic substitution. Doesn't ask us that, but that's what it is, to form the nitrile. Okay, now they are pretty picky about the conditions that you use for this. Well, but you know, basically what's going to happen, we're going to get a cyanide group coming in here, aren't we? And that's going to go there, and the chlorine's going to come off. But the conditions you need for that, you need KCN dissolved, and you've got to say this to get the mark, in water and ethanol. And they're always quite adamant of that. You've got to say in both of those. Okay. Now I think you can't have it just dissolved in water because water is pretty good nucleophile as well, and so you'd end up swapping the Cl for an OH, and you get the alcohol, and you don't want that. You can't dissolve it just in ethanol. I don't think it's too soluble, so you could have a mixture of ethanol and water. But they're not asking why, but they are the conditions. Okay, I'll remember that because they won't accept anything else. Right, and then the final step, we have got to turn that. We've got to reduce that into the amine, and the conditions for that are hydrogen plus a nickel catalyst, or you can use lithium aluminium hydride. Again, just be careful with that. If you say lithium aluminium hydride, you've got to say in ether as the solvent. If you just say lithium aluminium hydride, I think it's probably 1 mark going for it, and they won't give you the mark unless you say it's in ether. That's a reducing agent. Okay, so that is the end of that paper.